Director of Youth Center that you know already from the conference, Michele Calvi, and the President Riccardo Pietravisa. However, we want to gain time. So rather than getting you to wait for the introductions and then we run a test, we'll do it the other way around. We'll do a test straight away, and Francesco Graziotti was just going to introduce it very quickly, what we're about to see. We'll do a test straight away, and then as the lab technicians and engineers process the results of the first test and define how the next tests are going to take place, we will talk to you a little bit about Youth Center. So as I was saying, the president of Youth Center, the director of science, will talk to you a little bit about, but first, let's get the test running so that we gain time. So, Francesco, is there anything you'd like to describe about the test before we get the run?
Good afternoon, everyone. Just 2 words before the test begin. So today we are testing, as you see, a gable wall. What is a gable wall? Is a triangular wall that actually closes the roof, and it is a load-bearing gable wall. So basically, the timber joists are supported by the gable wall. And sorry, may I have the pen, please? Okay. As you can imagine, gable walls are relatively vulnerable or very vulnerable, and this is what we want to assess. Just a single word on our input. So what you will see today is actually a floor motion that was recorded in a monitored school in Central Italy in 2016. So it was very near to the epicenter, so 4 kilometers from the epicenter, magnitude 5.9. And this motion, so at the base, had a PGA, so peak ground acceleration of 0.37 g, while a peak floor acceleration, so the acceleration that you will see at the base of this system, is 0.55 g. I will go into the setup later on. You will see that also an amplification at the top, and then I will explain to you. Pippo, sorry. Okay. Are we ready? Okay. In the screen now we need another minute. In the screen you will see on top the 2 displacement of the 2 shaking table, and at the bottom the 2 acceleration, so the time history of the acceleration. Okay, as expected, in this run, we didn't have any collapse. We will see hopefully a collapse later on in the afternoon. Now, a couple of number. We had the displacement on the base of the shake table of about 40 millimeter, and at the top about 80 millimeters. So we had also 40 to 50 millimeter of differential displacement. And the acceleration was 0.55 at the level of the floor, and around 1 g at the level of the ridge beam. So now the guys are marking the cracks and prepare for the next run. And in the meanwhile, I will try to explain you briefly how the setup was designed and why, and what we are doing in this project. And then if you have for sure any question, right after. Non va. Ah sì. Okay. So it is for sure is something not new that the buildings are acting as a filtering and as an amplifier of the earthquake motion. This is a picture by Nigel Priestley of 1985, and basically the upper story masonry walls are particularly vulnerable because they are generally loaded with a very low overburden force, and the acceleration is higher at the higher levels. If you think about a gable wall, this is even more, this vulnerability is even more pronounced because you have a very high acceleration demand at the top level, very low overburden force, and on top you have a very high, or you may have a very high differential displacement due to the flexibility of the roof. That's why if you go in any post-earthquake survey, you will find lots of this type of structure or structural element collapsed. Despite this fact, in literature, there is no, substantially no study on the behavior of these structural elements. The only study that addressed exactly this phenomenon was a study conducted by us, and that we performed this type of test in LNEC, sorry, in Lisbon. As you see in that shake table test, we simulated the entire roof, but we had no control of the actual acceleration that we were applying at the ridge level. So we applied the floor motion at the base, and then the flexibility of the roof was doing the rest. What's the innovative thing of this test that we are doing today is that we are controlling the acceleration that we want to impose. And as you will see, we have, as I will tell you, we will have 3 nominally identical specimens, and we can systematically try to identify the contribution of different things, as the acceleration or the displacement. This is the setup, basically. We can start, yes, this is the setup. We can control differential motion, as you see. We have a very known boundary condition. This is very useful to facilitate the numerical interpretation of this type of test. For example, we have constant or almost constant overburden force due to the presence of, when you will see after the test, due to the presence of springs that are actually pulling the timber elements. The idea is this one. So you will have to also to add the acceleration, but the relative displacement that we are going to apply is something like that. So we have a linear amplification of acceleration with the height, and we are maintaining constant the overburden load. As I told you, we have 3 tests. One that we performed last week has the idea of simulate a perfectly rigid floor, or let's say a sufficiently stiff, roof. So a sufficiently stiff roof, and we already done last week. So acceleration at the base equal to the acceleration of the top. The one that the test that we will see with this aperitivo tonight is with an amplification of the top acceleration, but in phase with the accelerogram that we are doing at the base. So we are considering a sort of semi-flexible roof with the same, ideally the same period of vibration of the structure, something like that. And the third one that we will conduct in the in Italian summer, so I guess in a couple of weeks, will be with a completely decoupled accelerograms. What I mean for completely decoupled. So basically we will apply the floor motion, and then we are simulating a roof with a certain period, like 0.5 second, that is moving also out of phase in some part of the test. As you see, the specimen is heavily instrumented. We are using 19 triaxial accelerometers. From these accelerometers, we can also compute the force capacity of the wall, so the inertia force that is applied to the specimen. We are using 28 wire displacement transducer. You will see later on when you will pass by, there is these gray boxes with this wire, and 10 standard displacement transducer. On top of it, we are also using optical acquisition system, three-dimensional optical acquisition system. Unfortunately, today, since we have the open curtain, for this specific test that you will see, we have to rely only on the classical acquisition system, because the 3D system is not working with the open curtain. But for you, we decide to do our best also with the traditional system. In fact, this type of test, the acquisition system is pretty redundant, so we can have the same information from both sides. This is the earthquake. Sorry for the repetition, but maybe now we have a minute more to see the spectra. So this one, the dashed one, is the spectrum recorded, the spectra calculated from the recorded accelerogram on the ground of this school during this event. The black one is the floor accelerogram. Oh, this is wrong. The black should be, okay. Sorry. The red one is the one at the floor, and is referred, I don't know why, because I did a mistake, it's referred to the black one there, so it's the floor one. The other one is what we expect for the roof, so another amplification of 2 times. Today, I will not see exactly all the numbers that we will see, all the acceleration for the later test, because we are also organizing a blind prediction test, so a blind prediction contest. If you go on this site, you will have all the information. In reality, the context is about the prediction of the response of the first test that we already tested, as well as the other one that we will test in 2 weeks, so not exactly this one. In any case, the recording of today will be make available also to the competitors in this website. This is how we transported the specimen. Some of you asked me this, so we prepared this video to show you how actually we transported the specimen. We really, actually the last specimen is this one, so you see. We packed the specimen when compressed with threaded bar. We lift the specimen, we put on wheels and rails, and then we actually push the specimen in without dismounting all the setup every time. This record this video is, I think it was last Friday, so 1 week ago. And so then the specimen stayed there to wait for you for the entire week. Then there is this video. It's pretty long, but we can speak also about other stuff while he's going. But it is very important to understand how the setup is made. So basically, and as you see, we will have a dedicated presentation about the system. So this 9D double shake table system. But in general, basically, we actually applied this structure in order to have a motion, a differential motion, on each of these timber purlins. So we mounted all the system. As you see, the system is able to rotate top and bottom. Then we transported in the specimen. remove the wheels. Attach the specimen to the shake table. Insert the timber beams and load the timber beams via springs, wide springs, because basically with small elongation that we will have due to the motion of the setup, the force remain quasi constant. Once the springs are loaded, basically the wall is safe, so we could unpack the wall, and this is the system working. One second, I forgot to mention that these tests are performed in the framework of this RIS Supreme project. We will have a presentation by Dr. Riley at the end of in 1 hour on the RIS project. The name of this project is Supreme. Don't ask me how it's possible from seismic out-of-plane response of masonry gables reach to Supreme name, but we have to ask Dr. Sharma from TU Delft about this. And I think that we are almost ready for the next. Yes? Okay. We are almost ready for the next, so this will be slightly higher, say 25% higher in acceleration. And that's it, basically. And if you have any question, since we are waiting, please feel free to ask me. No problem at all. Yes. One sec, we have another microphone. Lì in fondo, mi sembra.
Thank you. This is very, very impressive. Could you describe the actuators on the top and just say what they're doing? Are they stabilizing it during construction? How do they move during the testing?
Yeah, okay. So the system the system, so the 9D shake table will be described in another presentation, but in general, these actuators are moving the upper shake table, let's call a roof table or roof shake table, and they are controlled in order to impose the acceleration time history as well as the displacement time history that you want to simulate. Okay, it's like a suspended shake table. Sorry, si è rotto tutto. Ci siamo? Boh, andiamo. So as expected, during the previous test we noticed some damage, and we saw the damage with slight crack on the specimen, but the real detection was instrumental. So we actually saw that the elastic behavior that we saw for all the morning, because we started early this morning, we detected there is a nonlinearity. So now, from now on, the test will be more and more interesting. Why I'm telling you early morning, because this is the team yesterday at around midnight or something like that. So just to tell you that we are very strong and supreme. Okay. Now we will be ready in really few seconds. So as I told you, this is about 25% higher than the previous one. So we will expect something like, I'm guessing 0.7 G at the base and the double on top. Okay, yeah, the test, this run is over. We will do other run later on in the afternoon. The only thing that I forgot to tell you, to mention you, is that the anchoring between the timber and the gable is absent. There is not a mechanical anchor, but it relies only on friction between the timber and the masonry. There is a layer of mortar. Okay, so I guess that we can, in the meanwhile, that we can, we will detect damage and do our stuff here. I will ask, I don't know what's this, the next.
Now I do it.
Okay.
Right. Sure. So what I'd like to do now is to invite Professor Riccardo Pietravisa, who's the president of Youth Center, and will now do this late welcome to Youth Center.
Okay, thank you, Rui. Thank you, everyone, to be here today. It's a great pleasure and privilege that you attend to this test. The test will last some time, so the machine should be reset every time. Youth Center, perhaps for many of you, is the first time you are here in Youth Center. Youth Center is a foundation that will have 20 years next year. And we perform both experimental tests and numerical analysis for the safety, in particular for buildings and non-structural elements. We have very particular devices. One of these is this one with this particular setup with double table, and we have another larger in the other laboratory we will see soon. The center is born thanks to Michele Calvi. Where is Michele now? I don't know. Michele Calvi is that guy, and that guy is Michele Calvi. was the founder and the inventors of every equipment that is here in your center. And your center has been founded thanks to 4 Italian public bodies. The 2 universities in Pavia, one is the University of Pavia, very ancient and important university in Italy, and the second is USE. USE is a University School for Advanced Studies, which is here in Pavia. I am also the rector of USE. And the Civil Protection Department and the Institute for Geophysics and Volcanology. And we like to play an important role for the safety of the country. As in Italy, as you know, there are a lot of earthquakes, and we play also an international role for testing, in particular for testing a lot of different industrial equipment for the safety, for reduction of the damage of buildings and of non-structural element. In Pavia, as you have seen during this week, we have a lot efforts during the last years to develop strong knowledge in earthquake engineering, both from research going to education, but also we have realized some small companies and startups that apply all the knowledge developed here in order to generate impact in the society. This is a global way that goes from the real scientific approach to the application for the safety of the society. So it's a very important path that we perform, and many students and PhD have studied here in Pavia, and now are professor all around in the world teaching earthquake engineering. So we are very proud of this story of Pavia Earthquake Systems, University of Pavia, USE and Eucentre, and the startups and spin-off that has been founded here. And I think that we now represent one of the fundamental points of the network, international networks. And the conference at which we have attended this week, thanks to many of us that contributed to the realization, Rui Pigno, one of that surely, which is also vice president of your center foundation, have obtained, I heard, a great success. So I want also to thank all the teams of your center that contributed to the success of this event, and I thank you for giving an applause to the teams of your center. Okay, well, thank you again, and give the floor to Rui. Michele Calvi, detto Mike.
Fai andare tu le slide come ti pare, perché tu
la slide della presentazione.
Tiring week. I've been asked to tell you a few pieces of information about the various laboratories we have here. So this entire story started about 25 years ago, as Professor Pietrabissa just reminded. And the first testing device was a single degree of freedom shaking table in the other laboratory. You can go directly to, okay, this shake table here, which is in the other laboratory. If you go around the building later on, you can see it. This is a very simple shaking table, 1 degree of freedom, about 30 tons of weight, about 6.8 G capacity of acceleration without mass. And of course, the acceleration capacity depends then on the mass and diminishes. But you understand that 6.8 times 30 tons is about 2,000 kilonewton force capacity. That shaking table can go to 2.2, is running some tests, 2.2 meters per second velocity and can go to 1 meter displacement. So simple but powerful. It was the starting point of everything. On that shaking table we have been performing many tests on different structures, even up to 4 or 5 stories full scale. Now on the shake table in the other laboratory there is a masonry tower. I'm not sure, about 15 meters tall, something like that. Yeah, 14 meters tall, something like that. It has been already tested. It will be tested again. It will be tested again in this month. And the peculiarity of that case is that there is an active mass damper mounted on top to try to control the response of the tower. In the same laboratory on the other side, we also have a three-dimensional reaction system which is made with cubes that are connected only by means of post-tensioning cables. So they are prefabricated cubes, 2.4 meters side, and this has permitted to have a very precise, very accurate structure. And we can use any sorts of load on that structure. Most of you are familiar with this kind of issues and of experimental testing. This is, you can see, is a full-scale test on a joint you can see with a number of degrees of freedom control and so on and so forth. The concept is similar in the sense that simple. We had at that time an hydraulic system, a pumping capacity, and of course accumulator. Accumulators are used everywhere here because normally we do not need more than, say, 30 seconds or something like that of full power capacity. So we use a lot of accumulators that are put under pressure and then can release their capacity of oil flow for a short time. This oil flow, today we are in the range of an oil flow capacity of about 30,000 liters per minute, which is an enormous oil flow capacity. This is essentially controlling velocity. Then in the other laboratory, we designed and constructed a testing rig for large size isolation devices. This kind of equipment is working almost every day because isolation devices are taken here from all over the world. There are a few very big now in the laboratory. This kind of devices have some sensitivity, so they should not be photographed or something like that. But anyway, that ring is a ring where we can have up to 50,000 kilonewton vertical capacity. This vertical capacity can be controlled at 0.4 meters per second velocity vertically, and this can also be controlled in the two rotation around the two horizontal axes. In addition to that, we have horizontal actuators that could go, well, you can see to 2 meters per second velocity and essentially again to something in the range of 2,000 kilonewton. In addition to that, we have also designed, you see that now this is a kind of a cover leaf test. So we can also mount a second shake table, which is attached to the lower shake table, so that it can control the other horizontal degree of freedom. So that system is essentially a system with 5 degrees of freedom. The only degrees of freedom which is not used is the rotation around the vertical axis. But the main point is there is a capacity of controlling very large forces with a lot of accuracy in terms of displacement and rotation control. This is a damper tester, which is, well, you cannot see staying seated, but it is in the back of this laboratory. This damper tester, here the matter is capacity of testing long devices and with a lot of power. Is showing you different kind of you see dampers that have been tested with this with this element, you understand that the core is always the same. Large flow capacity, large capacities in terms of electricity and so on, and all the rest is a byproduct. The last, we also have a mobile laboratory, which is somewhere located here, somewhere, it's parked, and this takes advantage also of that power generator, that power generator is capable of producing 1 megawatt of energy, so we can, or power, so we can move it around and have the power where we need the power. This mobile testing rig has been originally designed to be able to test entire houses, small houses, so we can take around the capacity of about 6,000-7,000 liters per minute oil flow, and we go around with 4 actuators with 1,000 kilonewton each. Capacity that could be used in different ways, could be also used to test isolated buildings, in which case the capacity in terms of mass becomes very large. Let's go, okay. This is just a test in the other laboratory, which is done with the mobile laboratory, because we were using the other testing rig for other purposes. So what you can see here, these are 4 actuators that are, powdered with the mobile laboratory taken outside the laboratory. Okay, so we do a lot of things on site, a lot of kind of testing. We have some capacity of data acquisition and so on and so forth, but I understand that we should rather be quickly, so let's come to this testing rig here. This testing rig has been first is a 6 degrees of freedom shaking table. So the lower part, Greg, you are asking something on this, is a shake table. The shake table is operated by 4 diagonal actuators. So the 4 diagonal actuators can control the 3 degrees of freedom in plane. Under the shake table there are 4 pancakes that can only push, they cannot pull. The shake table is moving on top of these pancakes. Then there are 2 spring actuators. So before testing, like now, the springs actuators are pulling down the table so that the pancake are halfway in, so that they can then control the lower shake table in this way. So 6 degrees of freedom. What we did next was to design the upper shaking table. The upper shaking table is connected to the lower shaking table by means of these 2 hinged elements. So there is a hinge there, there is a hinge there, there is a hinge there, which means that the upper shaking table is forced to move vertically and in the 2 rotation in the same way as the lower shaking table, but is free in the horizontal plane. So we have designed those towers, which have something like 70 Hertz frequency to be completely outside the frequency of operation of the table. And those actuators that you see on top there, that are essentially oriented like the lower actuators, those actuators have 2 meters displacement capacity. So the upper shake table could be moved independently in the 2 horizontal direction and around the vertical axis. The purpose is essentially to be able to reproduce any couple of floors at any height of building without reproducing the building. So the purpose is essentially to test non-structure elements. Under this respect, this is a special kind of non-structure elements, but imagine that we could have an elevator, a pipeline, we could have non-structure walls connecting the 2, we can have a glass window, and this means that we can control independently acceleration, yes, but more than anything else, relative displacement. So we can have a relative displacement which is in this direction, and then have an acceleration in the other direction, which is what happens in reality. Clearly, there is some need of numerical simulation, because we have to know the input that we want to put in the two shaking table. Is that clear, Greg? Okay, so this is essentially, I'm sure that while I was talking, he was showing, Igor was showing you some tests where we were testing no structure elements on the shake table here. And I think that this is essentially what we have here, which has grown in time and now permits us to have something in the range of more than 300 large-scale tests per year, which is something that I don't think would be matched in many places around the world. Is that fine, Rui, or should I? Va bene? Okay. In 1 minute we will go for another test.
Yeah, here we go again. So we detected the cracks. Something is happening because we noticed a lot of cracks around the joist. We noticed some horizontal cracks in the specimen, and the behavior is going really into higher nonlinearity. I guess that we are ready. So now we will test something approximately 1.5 times the first one that we see. So again, it will be around 0.75.8 at the base and the double on top. From now on, something may really happen. One minute more, so I will tell you when you start your video, not to waste your memory. Mi dai tu l'ok? Mi dici tu quando andiamo. Okay, here we go. Okay. As you see from here, it's very difficult to read. But computer. We reach on top more than almost 2G on top. Okay, as a peak floor acceleration of the roof. Next. Jerry. Yeah, next presenter. In the meanwhile that we assess all the damage, next presenter is Dr. Ancora.
I give the microphone to me in a few seconds. I only wanted to underline that what you are seeing here is something where the acceleration is increasing, and this wall is showing that it's close to be invulnerable with respect to acceleration if the acceleration is in phase. That's why he was saying that in future tests there will be an out-of-phase application of loading in top and bottom, because actually this kind of structure is certainly more sensitive to relative displacement than to increase the acceleration. If you increase the acceleration, it can open cracks, but more difficultly it will fall down than if there is significant relative applied displacement. I don't know if you don't agree, please.
No, yes.
I don't want to jump into.
Okay, so thank you, Kiko, for that kind introduction. So I guess you can hear me at the back, right? I know it's quite noisy. I was down there, and it's quite difficult to hear. So as you can read on the slide, I'm Gerard O'Reilly. I've been working here at EU Center or in Pavia, let's say, for a couple of years. And what I'm going to try to do now is not talk about the labs or the test in particular, which you've seen enough of that already, but to give you some context of the general activities in which we are doing this and the kind of activities that go on here in Pavia, right? So you can see a lot of logos attached to the specimen. One of them is this thing called ERIS, and you can see it here behind me. And basically, this is a project that is funded by the EU. So it's, let's say, this research infrastructures. It's this thing called transnational access that we're coordinating here in Pavia. So together with Michele Calvi, who you've seen, I don't know where he went, but we're coordinating these activities. And this is one of those projects or one of those activities within this project, okay? So, thanks. So what is this project and what are we trying to do within this project? You know, what's going on here? So basically, it's a network of laboratories, and one of them you're looking at it right now here at the EU Center. So basically, all these laboratories around Europe, so you can see them plotted on the map right there, and also a wind laboratory in Canada. Okay, so what we're trying to do is do basic or frontier knowledge, fundamental research on a number of different topics in these laboratories. There's a lot of noise. Yes. Thanks. So a lot of different labs. But what are we trying to do in these labs? So we've got, let's say, a lot of funding from the EU, which is always gratefully acknowledged. We've got 4 years to do a lot of testing, and we're trying to, let's say, address some fundamental topics. Okay. Not to get into some details, but if you're interested in the project, the details are there. But what is it we're trying to do within this project? So essentially how this works is that us as a research, let's say, community, we present a proposal to the European Union and say we want to do some research on some fundamental topics. So we set up this structure called, let's say, research goals. We want to address these kind of goals with the research we want to do. And you can see here it's addressing losses, it's quantifying risk, and it's also green and sustainable development. We're going to, let's say, address these themes, these different research goals. And how are we going to do that? Where are we going to do that? We're going to do that on these different research areas. So the first one you can see here is the built environment. We want to address research goals like loss reduction in the built environment, critical infrastructures, and also things like advanced technologies and industrial facilities. So we're setting up a framework of a project for more projects, if you want to look at it like that. And as part of this project, it's actually a multi-hazard project, but obviously here at EU Center we're looking at earthquake engineering, but just to say we have partners looking at geotechnical and also wind engineering, okay? So some of those partners you saw on the first slide on that map around Europe and also in Canada. We also have some wind tunnels and other kinds of facilities within the consortium. So to give you an example, what we're looking at here is all of these little sub-projects within this bigger project that we're coordinating here in Pavia, and they try to fit in this whole overall structure, right? So to give you an example here, I've put some text on the right-hand side of the slide, but it's probably a better example to refer to what we're actually looking at here today, is that this is, what are we looking at here? Is we're looking at a gable, so we're looking at the built environment, we're looking at earthquake hazard, and we're trying to reduce the losses because of earthquakes, obviously the out-of-plane collapse like you saw in central Italy, and also quantifying the risk of this out-of-plane collapse. So these smaller projects fit into this bigger scheme of things, and there are dozens of examples we can see with this kind of framework. So this has already been presented, so just to go through it again, so I'll go through it very quickly, is that here at EU Center, obviously you've seen there's a number of facilities here available, the big shaking table, the one right here behind us, the mobile shaking table, strong wall, and so on and so forth, the bearing tester. But as part of this project, what we're doing is we're saying that external users can come and use a certain portion of our facilities. One thing I forgot to mention is this is something called transnational access. So what it means is that all of these projects that I'm mentioning, this is for external users to come and use and perform research here in this laboratory. So actually, even though we're here testing this stuff in Pavia, you can see there are a couple of logos on the specimen here, and this is being led by TU Delft in the Netherlands. So this is really a Dutch group that's leading this project. They're coming here with the support of the EU which is basically covering the funding to do these tests here in the laboratory. So let's say it's giving the opportunity to researchers to try out niche ideas, new ideas that fit into a bigger picture, free of charge. That's the basic mechanism here, okay? And what I'm showing on the slide here is just some of the possibilities that we have here at EU Center. So when people contacted us saying we want to be involved in this project, these are some of the possibilities we were showing to them. So you can see here the 9D shaking table, which Professor Calvi has just shown a few moments ago. I won't spend too much time on that. The same video again. Some dimensions as well. Also the mobile shaking table, which you've seen just a moment ago. If I'm not mistaken, it's parked around the back. But and these are just some technical specifications that I think you may have seen already. So, like I mentioned before, this is a project with more projects in it, and with researchers from all around Europe and all around the world as well. Okay, so if we just look at this map, who's actually involved in this? So we can see we have a number of different laboratories, both in Italy, Portugal, France, the UK, and so on and so forth. Also in Greece and North Macedonia. And we can see that we have. We can have the involvement of a lot of different countries. So these are all the different laboratories that were within our consortium that were giving access to these external user groups. So if we take a look at then of the actual applications and who's involved in this, we can see just some general numbers of how many people are trying to be involved in this, and let's say the competitiveness or the interest in these kinds of activities. So you can see the number of different calls for proposals. There's a lot of interest around Europe, a lot of different research groups. I'll show a map in a second, which is maybe a bit more intuitive, but you can get the general idea, okay? And you can get a general idea of the number of applications we received looking to do work on earthquake engineering, wind engineering, and so on and so forth. So if we look just again at the map of where all these labs are located, and we look at, something happened to my slides, sorry. I'm going backwards, that's why. If we take a look at this map here, this is showing us all of the different groups that are involved in this project. So basically with this funding, this structure, and this opportunity, people from all of these places all around Europe and all around the world were interested to come and perform these tests. So like I mentioned before, this is a test based with the group based in the Netherlands, but also has some interaction with some other partners around Europe as well. So this is for all of the different projects we have in this bigger scheme that we're coordinating. So we can see there's a lot of work and a lot of experimental data is being produced here as well. So this is probably the biggest input, or the biggest thing that may be of interest for you here today, is that the amount of experimental data and output and findings that will be produced as part of something like this is going to be quite numerous. Okay. And you can see you can't really understand much from a diagram like this, but it conveys the overall international collaboration, which isn't always easy to achieve. So this is the first and second call. We do the same thing with the third and fourth calls for proposals, and the same kind of idea here again. So you can see there's a lot of interaction within Europe, all of these different research groups from various different institutes, but also from North America, Oceania, Asia, and so on and so forth. So there's a good opportunity for people to collaborate, come work, and use facilities like these here. So I don't think I need to repeat the uniqueness of the shaking table we're looking at here behind us, the different kinds of capabilities, capacities, and flexibility of what it can perform. So with this, I think I'm going to close here, but it's just to kind of give you an overview, a bigger context of what it is we're doing here. I know everybody's excited to see the wall and see, hopefully it's going to come down and break in the next run. But to kind of give you an idea of the bigger picture of what it is that's going on here at the EU Center, I know there's a lot of volume in terms of the amount of testing that can happen, but to kind of give you a bigger picture of what it is and why we're doing this and with whom we're doing this. So that's mainly what I'm trying to show you here, okay? So I'll pass you over again, I guess, to Professor Calvi, who is...
Since Rui is on the phone, I suggest that now we go and have a quick look at the other laboratory, because we are expecting that either this text or the next one, this structure will collapse. So they will take away a number of instruments that we do not want to destroy, while we go and have a look at the other laboratory, and then we come back. So please don't go around for hours, but how long? People, dove sei? Quanto tempo ci vuole a tirare via gli strumenti? Per quanto tempo devo tirarli in giro?
Almeno un altro quarto d'ora.
Okay, so we should be back here in 20 minutes. Okay? Ready for the next test. And we go around here to have a look at the other laboratory.
Okay. Well, let's wait another minute. Okay, so welcome back. We checked the specimen. From the crack pattern and from the data that we acquired, we noticed that we reached the strength, basically. So the mechanism is free to move. Now it's a matter of understanding how the collapse will take place. This run or maybe the next one, we'll see. For this reason, since there is a relatively high chance to have a collapse now, we remove some of the instrumentation. So we remove some accelerometers and we remove some wire potentiometers. So the boundary condition is fully monitored. The boundary condition is fully monitored, but we remove some accelerometer from the gable itself to save some of them at least. We are ready, so okay, let's go. We are giving something like about 1G at the bottom and 2 times on top. Okay, as you see, yeah, we didn't have the collapse, but we were really almost there. So maybe next one in say 15 minutes, we will have the last one. We have to yeah, we need some patience for this type of test. Can you imagine the quasi-static one? How much patience you need? So let us check the cracks, see the data, and then we do hopefully the last one.
Okay, I think that in the meantime, Dr. Morandi will give us a short presentation of the bell tower project you have seen in the other laboratories. So meanwhile, technicians and engineers will keep going, checking the signals and crack and so on and so forth. So Paolo, you have all the time while they are checking.
Yeah. Okay. Okay, some additional words on this experimentation of full-scale bell tower. So first of all, I have to thank, of course, also Isaac and Mapei, which are the founders of this research. And of course, this research is carried out at the U Center, but also with the collaboration of Professor at the University of Pavia of use. Okay, so, the motivation and objective, bell towers are frequently damaged by earthquakes and, of course, require interventions. We have, several cases that during the last, earthquakes, also in Italy, that we experimented really a lot of damage on the towers in general and the bell tower in particular. So the other main, of course, motivation is that we are plenty of towers and of bell towers in Italy, but also worldwide. Just to let you know, in Italy, it's assumed to have more than 50 or 55,000 bell towers, but maybe even more, because not all have been estimated. So, of course, on the bell towers, in general on the towers, there is a lack of systematic scientific studies and research. And of course, there are no or really few tests on real scale masonry bell towers, in general masonry towers. So Isaac, which is an Italian company which is based here in Milan and who developed seismic AMD, so active mass damper, came to us saying, okay, we want to test such type of devices on masonry structures. So we thought that a good structure could be a tower, okay, because of its relatively low mass and relatively low frequency. And this is what we did. So first of all was, as I already told you 5 minutes ago, we did the statistics in order to, design the tower. So through the statistic, we see that in some region in Italy, the average height of a tower is of a bell tower is about 19 meters, and the slenderness is about 5 to 6. So that means that we have a laboratory constraint, which is the height, maximum height of the tower, that ends up to be 12 divided by 5.5, a side dimension of about 2.2, 2.3 meters. So this was the basic idea to design this tower. Of course, we had some towers as a reference. This is just a typical tower of, let's say, north and central Italy, made by brick masonry. And this is the design. This is a prototype, scale, let's say 1:1. Of course, is small as respect to usual one, but it can representative by real scale tower. I already described a bit the type of the tower. Here you haven't seen it because we removed, but we have also two bronze bells of a diameter of about 70 centimeters, of a weight of 170 kilos. They are blocked, so they cannot move, cannot tilt during the test, because we think that this is the worst condition, because if they move, maybe works like damper itself. And then the type of masonry, it's a typical clay bricks with a mean compression strength less than 20 megapascal, typical of existing masonry structures. And we had produced a specific time-on-line mortar, hydraulic line mortar, with a mean compression strength less than 1 megapascal. This is possible with a particular type of mixed design. This is just, some details, our reinforced concrete foundation in timber floors and roof. I don't want to be too much in detail on that. We did, of course, test our mechanical characterization, and also we design and construct a scaffolding for safety, of course, for safety reasons. As you see, the tower was placed exactly in the center of the shaking table, and as you know, in this case, the shaking table in one direction only. This is just some construction details of the bell towers. You can see here, the ring beams, the narrow windows, the timber joist, the lintels of the structure. I would like to show you a time lapse of construction. It's pretty interesting because we constructed it in 5 weeks. And I have to say you that as respect to drawings, the error in height was of 2 centimeters. So congratulations to the constructor, which is Damiani Costruzioni, that really did a very good job. So it was pretty quick to reach the top, with the exception of the bell chamber, where of course we had to do details of the columns, of the arches, with the arch formwork, and of course also to lean the roof, the timber roof. So this is of course a very quick time lapse, and that's it. This is the final specimen, as you can see. So 2 words on Isaac and on the AMD devices. Active mass damper are, much better than me. Masses move my mechanical system, whose oscillations are controlled electronically in amplitude and in frequency, and of course are based on acceleration experience in the structures. And of course, another important ingredients is that the system is non-invasive. It should be reversible for, of course, restoration needs. This is just some pictures of the machine placed on the top of the tower. Of course, below the machine, at the level of extra docks of the floor, we had to strengthen the floor, okay, through topping, a concrete topping, which was anchored at the peripheral sides of the bell tower, in order, of course, to get rigidity and strength enough to, transfer the forces of the system to the tower. Okay, what we did. First of all, dynamic characterization test on the bell tower before and after, of course, each run. And then the phase of dynamic test is so there are two phases of dynamic test. The first phase that we already performed 2 weeks ago, the bell tower in its current state and the bell tower plus the AMD system. Then we have cracked a bit, as you have seen, and then the phase 2 in a couple of weeks' times will foresee the repair strengthening techniques and also the system. The accelegrams that we used is the 2012 Emilia earthquake, and this is okay. The instrumentation that we installed, I already talked about that. It's nothing of particularly interesting. Okay, what is more interesting is the loading protocol. We decided to use the May 2012 main track of the Emilia earthquake, 2012 east-west direction, with a PGR of 100% of the ground motion at 0.26 G. So the idea what was to test the first part of the test with the AMD on, in order to limit the damage and the cracking, up to the fine point where we believed that the amount of damage was enough, let's say, so not too high, not too significant. Then we switch it off and reproduce the same intensity, the same protocol, okay, so scaling up the ground motion up to, in this case, 60% of the intensity. And then we stop it when a moderate level of damage occurred. This is just example. Look at on the left the AMD off and on the right on at 0.13 G, just, very rough example. They are not, look at the top. Look at the top. How big was on the left the displacement at the top, and how smaller is the displacement with the AMD. I will have other perspectives. You can see there, okay, there was starting a cantilever flexural mode, followed by a rocking mode. And you can see also focus here on the chamber, bell chamber. Look at that, how big it is, and look at the velocity, the frequency of the movement of the AMD. The nice thing is that also when the AMD is off, was also torsions of the upper part of the bell tower, because there was a crack on the arch. I will show you later on one of the two arches, and so there was a torsional and asymmetric behavior. You can see just an example in the case of 16% of the ground motion with the off, with the AMD off and on. You can see here a displacement of 37 millimeters and 47 millimeters, but when in on, the displacement reduces of between 2 and 1.5 times. So this is good. And also the displacement shape is more, let's say, uniform, but when it's off, there is more concentration of deformation in the top part of the tower. Here, just some damage pattern, from which is okay, of course, concentrated at the base of the tower and at the base of the belfry. And interesting things is also this one that we made help from drones to detect the damage also in the upper part of the tower. This was very, very good, and this was the damage occurred at the extrados of the arch, as I told you before. Then we stopped it, and we provided strengthening interventions with FRCM at the level of the belfry. So we made, FRCM through Mapei, with Mapei at the corner of at the two sides of the 4 columns, of course, in correspondence to the floor, so about 1.5 meters and 1.5 meters, in order to increase the capacity, the flexural capacity at the base of the column, and also in all the internal part of the chamber. And that's it, actually. This is the situation as you have just seen, and we have ready to redo this second phase of the experiments in a couple of weeks. So that's it. Thank you very much for your attention. If there are questions, I'm available. Almost ready for the next test. There are guys on the table. Okay. We don't care. There are questions. Yes, please.
I want to know that how old are this tower, age of this tower, and are you trying to simulate when you create a brick? Is it in that focus or not?
So the height of the tower is about 12 meters from the base, the height, and of course we are simulating with numerical analysis the Yeah, good question. Age of the towers, it depends. We have a lot of ages that ranging from 100 years up to several centuries. So there are even some towers of the beginning of 20th century, so more than 100 years, and some others that have been 200, 300, 400 of years.
Thank you for your presentation. Just one question about how you treat the bells up there. It's very interesting. So you have 2 bells up there. They are 340 kilogram in total. And then you said that you fix them up there. So, and then you mentioned it's like the worst scenario. So it's like an added mass up there. But if it looks like to me like it's only other end of the real situation, because in real situation it will swing, so it will kind of work like a 2 mass dampers, something like that. So I understand this is like a worst scenario, but how far is it from the real situation? So would you say that your result is like over conservative in this case? Thank you.
Good question. You're right. This should be probably a conservative situation. We don't know how much is conservative. We can do that. We can estimate through numerical analysis. But the real motivation is that we wanted to add uncertainties, complexities in a test like that, which is already a lot complex. That's the main reason.
So from the explanation near the tower, I understood that you just blocked the bell, not you removed it.
Yeah. The bells are blocked, are completely blocked. Now they are removed for strengthening reason, detail reason. Yeah, exactly. Yeah. So I think the test is ready. So okay, I pass the word to.
Yes. So we check the crack. We have a lot of residual sliding, more than 2-3 centimeters. The cracks are open, so now we will see what's going on. Okay, let's go. Finally, we can have the aperitivo now. So now the program is, I'm asking to the Rui, aperitivo. So you simply walk in that direction. Thank you very much. If you have any question, we can speak during the aperitivo.